Oh, yes. So I'm James. I'm actually not the first speaker, but I thought I'd just introduce myself personally before we get started. And check out the cool audience, see if everybody looks like they know what they're listening to. So what I do is I look after the roadmap for the product at DDN, and I also manage the benchmarking group who tests out various systems, including GPU systems at rather large scale. And we also work very closely with NVIDIA within my team to build the reference architectures. By the way, just out of interest, who in this audience have heard of DDN? Okay, nice. You actually chose to be here. Good. Very good. Okay, so I'll hand it over to Jacob and I'll see you in a few minutes.
Can y'all hear me okay? It's good. My name's Jacob Lieberman, and I'm very grateful to be with all of you today and here presenting with James. Like Rajat mentioned, I lead a product team at NVIDIA that builds Gen AI solutions, and I also, about a year ago, kicked off an initiative called the AI Data Platform. And so we'll get into that a little bit, but it's something to kind of prepare and bring enterprise storage and data platforms into the realm of Gen AI. Is today St. Patrick's Day? Is that? Oh, and so, yeah, happy St. Patrick's Day for those who observe. But yes, I love the holiday spirit. Oh, we just did that. That's us. You can verify because our faces are right there. So NVIDIA and DDN have a very, very long history together that goes back several decades. In fact, when I worked at Dell way back when, and I was an HPC performance engineer, one of our first solutions included DDN storage with NVIDIA GPUs on Dell servers. And what we've seen, and the reason that this is, I'm going into all this timeline, is that over the past decades, what used to be kind of relegated to fringe scientific computing at very extreme scales, HPC, has steadily made its way into mainstream enterprise computing. Are there any HPC folks here? Okay. So you're probably the same folks who have heard of DDN, right? So this is a pattern that we're seeing play out over and over, where research innovation, fundamental research innovation, the kind that's done at universities and government research centers, actually become the innovation that drives mainstream technology adoption that we're all benefiting from today. So I'll just touch on a couple of these points, but in 1998, there was a standards body that defined subroutines for basic linear algebra kernels, and that was called BLAS. And one of those kernels, and I'm not going to nerd out with you guys too much, but one of those kernels was called DGEM, which is a double precision matrix multiply, and that algorithm became the heart of everything we're doing today with tensor cores for Gen AI. So that was born in 1988. So it's probably older than some of the people in this room. Around the same time, maybe 10 years later, the Lustre file system was born at Carnegie Mellon, and that was one of the first open source parallel file systems that could really feed data into CPUs in these massive computing clusters at a high rate. And Lustre is the foundational open source project on which DDN built their technology portfolio, and they were very involved with Lustre from the very beginning. If you fast forward about 15 years, and if you go by HPC as an indicator of success, in 2016, 70% of the 500 fastest supercomputers in the world were powered by DDN storage. And within about that same time frame, there was a tipping point where GPUs surpassed CPUs as the dominant compute platform on these systems. If you move ahead another 8 or 10 years, these technologies have come out of research computing into mainstream enterprise computing. Currently, there's, if you heard Jensen talk about it yesterday at length, basically everybody is using accelerated GPU compute now, mostly from NVIDIA. We estimate that there's more than 40,000 companies building and working on our platform. And similarly, many places where you find our GPUs, you find DDN storage. There's over 1 million NVIDIA GPUs connected to DDN storage today, and it's growing very quickly. So we have a long, long shared history and pedigree of working together, and in the minds of many folks, DDN is to data what NVIDIA is to compute. So the dominant workload right now in enterprises is not the technical computing that they were doing in HPC, it's Gen AI. And Gen AI means a bunch of different things, but generally speaking, whether you're training a foundational model, you're fine-tuning a model, you're serving inference, you're retrieving context via retrieval-augmented generation or cache-augmented generation, you're using prefill KV cache. Basically, whatever you're doing with generative AI depends on rich, accurate context in the form of data. So data is still king. Maybe we've forgotten that somewhat in all of this enthusiasm about Gen AI and the capability, and these models can talk like us. But at the end of the day, it all depends on fast access to high quality data to teach the models the things that they didn't know the day they were born. So there's just a few examples here, but roughly speaking, when we talk about Gen AI, we often talk about training and inference. Training and inference usually, or almost always, have a necessary data preprocessing, data collection, data cleaning part of the pipeline. That's absolutely essential. And it turns out that it's very difficult to do inference or training at scale unless you're also capable of preparing the data at scale. So this is a lesson that we learned at NVIDIA. So if you saw the keynote yesterday, Jensen mentioned this. He said that everything we do, we deploy internally first. We have one of the world's largest AI factories that we've deployed inside NVIDIA, and we have hundreds of agents on it, running workloads, doing our engineering work, helping us design the chips. Well, when we first stood that up, we knew how to do agents, we knew how to do all that stuff, but the thing we kept bumping into and hitting our head on were all of these concerns around data. Maybe we had 7 duplicate copies or conflicting copies of the same data. Maybe the access controls were getting disconnected, and it turned from the source of truth documents. And so, generally speaking, in addition to the pipeline complexity of standing up a large-scale data center scale training or inference infrastructure, the rest of the complications are introduced by data and how you manage data. So data complexity and sprawl, data is multimodal by nature, data velocity and drift. Your data is not a lake, it's a river. It is constantly flowing, it is constantly changing, and it's also growing. The tide is rising. Anybody in this room who manages data knows that. And then also data has gravity. Data gravity means that it becomes, the more data you have, the more expensive and inefficient it becomes to move the data around to do things with it. And these are the same challenges that we encountered when we were deploying our own AI factory, data center scale within NVIDIA. So I mentioned the NVIDIA AI Data Platform. This is a reference design for GPU accelerated storage. It turns out that many of these data preparation tasks benefit from GPU acceleration. And so what we learned when we were deploying our own internal AI factory is that in order for enterprises to adopt these technologies at a large scale, they can benefit from our suffering and learn benefit from our suffering and not have to learn these lessons that we had to painfully learn ourselves if we package these learnings with some of our most important partners and deliver them as capabilities. So with AI Data Platform, we take these pipelines and we deliver them as an appliance to reduce the time to insight and eliminate some of that pipeline complexity associated with doing it yourself. Our pipelines are state of the art. So if you look across many leaderboards, whether it's embedding, whether it's re-ranking, indexing, structured and unstructured data, agentic reasoning, our research teams make sure that our pipelines are state of the art and we're keeping pace with the rapidly changing development velocity in open source. So if you adopt our appliance, you are also getting on a train where we're continually updating the software and delivering it to you so you can keep pace. It's difficult. It's changing so quickly. It's hard for us too, but we're doing it, and then the customers who adopt the platform are benefiting from that investment that we're making. Another thing about the AI Data Platform is, like I mentioned, your data is always changing. We're continuously ingesting the data and making sure that it stays connected to the source of truth documents, those AI representations, the training data sets, the embeddings, the indices, the chunks. We make sure that those do not get disconnected from the source of truth, and they're continuously kept up to date. Your agents are only as accurate as the data that they are reading. If your data is not recent, your agents are making bad decisions, no matter how well they reason. And then the data gravity, we address that by moving the compute to the data and operating on the data in place. So I'll just show some of the, I'm running a little bit over for my section, but just to wrap this up, a typical storage network, these are complicated networks. The days of storage just being an array that you attach to a server, those are done. The storage networks are just as complicated as the AI factories that they're attached to. And generally, you have a CPU storage controller that's serving the protocols and protecting the data with things like erasure coding and RAID. You also have storage disk arrays where the data is stored, and these are key to there's trade-offs between performance and capacity. So architecting this part for Gen AI is also critical, and James is going to talk about that. But what we're adding is a GPU storage controller that is in the storage network and that can process the data in place to make sure that it is always recent, ready, and secure for your Gen AI workloads. So this is the new thing. And a picture of some of the economics. Oh, actually, I didn't put the economics in this slide. I have another session tomorrow where I go into the economics, so there's a little plug for my next session. But you've all heard about AI factories. Everyone's talking about it everywhere. I just want to give you a kind of a mental model of where an AI data platform fits in with an AI factory. So the technology we deliver, it goes from the edge all the way through the cloud. Everybody's using it. But the AI factory is where all the heavy lifting is done in terms of large-scale training and inference. And so in the future, what we are starting to see and expect to continue is that every AI factory will have an AI data platform, because there are economic and performance advantages to separating the data preparation from the training and inference. In the same way, if you're inference people, that if you separate the prefill from decode, you can scale and optimize them separately. That's also true for this. And if you're not familiar with those things, pretend you didn't hear that. But the benefits of this approach are, first, you can optimize your cost and efficiency. As your data grows, as your factory grows, optimizing the cost, the efficiency, and especially the energy consumption becomes a critical consideration. You can also decouple their life cycle and scaling. Everyone wants to consume the latest models right away, but nobody wants to be very experimental with their data path. They want to protect their data. If you separate the life cycle of these two things, You can innovate very quickly on the factory side and on the compute side and be conservative on your data path and protect that data. And you can also scale them independently. You know, what we found with our own internal factory is we're adding B200s or GB300 GPUs as our data grew to handle the data processing tasks. So now we're kind of misallocating these GPUs for training and inference to data processing. So actually adding an AI data platform gives you GPUs back. It gives you GPUs back for your training and inference. And last, it improves data security. This is critical. When you start making copies between your factory and a cloud between your data and the factory or a cloud or the edge, every time you make a copy, you're increasing the attack surface on the data. And those can become shadow or dark assets that you're not governing with the same policy that you do the rest of your data. So if you operate on the data in place, you're guaranteed that the representations of the data, the training sets, the RAG collections are governed and secured the same way as the source of truth data. So an AI data platform is a great way for an enterprise to get access to their data as an on-ramp to Gen AI by pulling it in as an appliance. And DDN has that with Supermicro as a hyperpod. And it's also the way you optimize the performance and cost of your AI factory at scale. So I went over. Apologies, James, but all of that was to tee him up. Thank you.
Thank you. Well, you did. Okay, so you all know who DDN is, so we can do this one quite quickly. We've been around for more than 20 years, building large-scale, high-performance storage environments for tough data challenges. We've had some very nice things said about us by Jensen. They chose DDN originally about 8 years ago for the first Selene system. As Jacob says, the AI factories are kind of built in-house first and tested extremely well. We've been very privileged to be a core part of that. Every time there's a massive iteration, then we see some DDN delivered in order to support those things. And we don't talk much about racks and physical systems. We actually talk a lot about software nowadays, but it's also still cool to see some systems. This is a screenshot from Omniverse, basically a simulation within NVIDIA. And just in the bottom here, if you want to see what DDN looks like, you'll see these cool looking systems at the bottom there. These are the data storage systems to support those GPUs in that system. And of course, this isn't a photograph. This happens to be a simulation, which NVIDIA uses to model new data centers, which is also very cool. So of course, we've provided the environmental specifications for these systems, and that's used within Omniverse to create a simulation of data centers so that we can build something that's going to work when we put it in the field. So DDN is a pretty stable, large company specializing in high-performance data solutions, particularly nowadays for AI, and we work closely with NVIDIA to build these large superpods or neoclouds and work in public clouds as well. And our primary purpose in life is actually to increase the utilization of GPUs and the efficiency of the utilization. So you'll find that this presentation is not really so much about storage, and it's an awful lot about essentially opening up the economics of GPUs. These are scarce resources and they're not low cost. So the more we can get out of them, the more productivity we can gain from those GPUs, the better. And there's a big hidden secret in the data platform that allows you to do that in myriad ways, which I'm going to explain in this presentation. So time to revenue, return on investment, cost per token, GPU efficiency, and power efficiency. Those are really the metrics we measure our success by in my groups, where we do the benchmarking, the testing, the reference architectures, we test real applications. We're not really, underneath it, there's gigabytes per second and IOPS and all this kind of stuff. But really what matters is how much output do we get from this model training? How much output do we get from this inference session or from this Spark data preparation workload in a given time frame, in a given set of watts or a given number of GPUs? The audience Feel free to look happy and excited or confused, and I'll judge where we are based on your faces. Excellent, confused looks there. Well done. So we think we're bottlenecked by storage, by the data environment right now. Of course, we know the models are doing amazingly, right? We're constantly amazed by new models, and we're pretty amazed, frankly, by NVIDIA's ability to push out new GPUs with bigger and better memory bandwidths, more cores, more performance, etc. And the bottleneck is increasingly in the data environment, because the more memory bandwidth you have, the more demand there is for that data. And there's lots of ways, lots of places where that data is being demanded, which you probably don't even notice in normal life. So it's quietly burning watts. We're quietly burning your capital and your OpEx because you can't see the fact that the data is arriving a little bit too slowly for every single operation, and that all mounts up into massive inefficiency. Today, we're mainly going to talk about inference, not interference, but inference. It's probably a good play on words there, but what we're trying to do is, for a given set of GPUs, a given set of watts, stop taking pictures of that. For a given set of watts, a given set of GPUs, we're trying to push out more productivity, more operational productivity. We're going to switch it forward now. More productivity from that given GPU. And to do that, of course, we've got to dive deep and work out what exactly is happening to the data environment during, let's say, an inference query. Where is the data actually being stressed? And I'm going to talk about that in this presentation and go a little bit deep in the 2 minutes I've got left. No, in the 10 minutes I've got left at least. So before we do that, I want to give you a couple of examples of where we start, because we don't actually start, trying to make the fastest storage in the world. We start with trying to understand what the real problem is and building, actually in conjunction with NVIDIA, building these pipelines. So maybe this one will play. Maybe you'll be able to see it if you sit at the front. Oh, can we dim the lights at the front, really? I know they can't, but I'm just going to ask anyway. If the lights were dim, you could see this right at the back. But what we're looking at here is actually an NVIDIA pipeline for raw media ingest, and then automated tagging, and then search. So imagine you're a smart city. You've got 10,000 video cameras, and you want to find an instant, a traffic jam, or a problem of high density of people walking around a street. In this case, we're looking at shoplifting. Then you need to build a pipeline, an AI-enabled pipeline, that's going to take all those streams, turn them into semantically searchable metadata, which you can then find out whatever you need to find really, really quick. So what you're looking at, by the way, we've installed this pipeline. I'll show you that in a minute. We're running it on the DDN data platform, and that data platform is doing kind of everything under that pipeline. We're handling the metadata, we're allowing to update it, we're handling all these semantic information that's being pushed out by these pipelines, which are provided by the NIMs from NVIDIA. And after we do that, we're able to, for example, find a video with a group of, does it say zebras? So imagine you're in a smart city and you've got 10,000 camera streams. Let's run that again just for fun. Then, ideally, you want to just type in what on earth you're asking for. And it might vary day to day, and you might not know in advance the kind of queries you need to ask for. So you need this extremely flexible semantic environment in order to build this. So here, by the way, we're ingesting a bunch of video files. Then it's running through a set of NVIDIA NIMs, a pipeline, and those are essentially adding context and adding that metadata. That video data itself and all the metadata that's being created is being pushed into the data platform. So it's one software data platform, not separate databases and separate object stores and separate file systems, one scalable software data platform, and we're integrating with that pipeline to provide this whole experience. And the benefit of this experience is twofold, really. It's performance and its simplicity. We've simplified that whole problem of how do we handle this database stuff, how do we tag, how do we search, how do we do all this efficiently, how do we extract the improved efficiency out of those GPUs by using a data platform. In this example here, we're actually searching for an example of when Jensen says nice things about DDN, and it found that video in 10,000 videos, and then we can put that on our website. So there's example one, and We're not going to go into super detail, but here's the pipeline that that's built on. And so you'll see there's the end data comes in from here, from these streaming cameras, goes through various NIMs, chunking happens, then the chunks get pushed into an object store, which is DDN's data platform. That's integrated with a vector database so that when the queries happen at the top there, those are both managed and handled through NVIDIA. We handle the metadata, we handle the objects, we retrieve the objects and push it back in just a few milliseconds. So that's one example of a kind of high-level workload that we try to accelerate. There's many of these. Here's another example. So here we're looking at RAG. So RAG is when you're running some kind of model, and that model needs to go out and add context from an external knowledge base to augment the query to give you a better answer. And there's two options here in this example. We can use the cloud or we can use NVIDIA. And there's going to be different performances in terms of the response time, the ingest time, retrieval time based on that. So this really is a demo for enterprises who already have data in AWS on the cloud. And we're basically comparing what performance you can get by replacing that with a very low latency data store on-prem. So it's really one of the choices. And we have about 10 of these pipelines across financial services, life sciences, video semantic search, robotics, manufacturing, all doing different things, comparing cloud with on-prem, comparing different NIMs, comparing local storage with DDN, comparing ourselves with competitors, et cetera, et cetera. So we do all of these things, and the goal really is to do two things, actually. One is to make life easy for our customers, saying, we've built these pipelines already. Obviously, you're not going to use these sort of as we provide them. We're going to adjust them, and we're going to give you a great head start. But also, we get lots of great hints about where the problems really lie in actual models in semi-production status. So here we are at the top. These are the applications and services, the pipelines, the examples we've just shown there. And then our engineers and the team in the benchmarking here, we work to build this hyperpod solution that has all the attributes necessary to drive up the GPU efficiency. So we run the pipelines, make it as real world as possible, identify and profile the workloads, and then optimize those workloads. And that really looks like this at the end. We're finding all these things. We're looking at the ingest streams, the labeling, the tagging, the normalization, the pre-processing, the upcalls, the ranking, embedding, transforming. All of these things we actually love. I know, it's unbelievable, isn't it? We love these things because that's where we can make a difference. When the GPU is working inside its memory and doing its own thing, we can't help. But when it's doing any of these things, we can help and we can drive up efficiency massively. So I'm going to give you another little video, which might be difficult to see, we'll find out. Just to summarize that before we look into some cerebellum level stuff, some real graphs from benchmarks to look about what we actually see in terms of the raw performance of these systems. Created by Anthropic about 10 minutes ago. Hopefully you can see this, but if you can't, I'll talk through it. So in this presentation, we're going to look at model load, which is the first thing you've got to do, of course, is load this model into GPU. And there's a discrepancy between doing it well, 92% efficiency, and doing it badly, 60% efficiency. And we're trying to optimize these, what turn out to be pretty much large sequential reads into GPU memory. And we do that in various ways, by the way. We've been optimizing that for multiple years. The second part we do is this vector lookup, this RAG, this context retrieval from external knowledge bases. And by optimizing that, we can increase the efficiency over traditional storage even further. And then finally, KV cache. Who's heard of KV cache in this audience? Context memory? It's about half. Okay. Yes. And then sort of thirdly with KV caching, which I'll explain a little bit later on, we can, again, improve the efficiency further. And this gap gets wider and wider. And in fact, this gap's getting wider and wider all the time because the models are going agentic. And agentic means more stuff happening and more calls into external storage repositories. And it gets harder and harder to maintain efficiency without a super efficient data platform. So really this graph, if you can see it, I did ask Anthropic to make it brighter, but it slightly failed. This graph, hopefully you can see that the efficiency with DDN, we obviously trying to keep that line really high against the competitors, against public cloud competitors, against non-traditional storage environments, etc. And that really translates into money. So super easy introduction to what we're trying to do there. And as I mentioned, this stuff is important because it's getting harder and harder. The Nemotron version 3 came out a couple of months ago, I guess, and it added a bunch of agentic capability. And here's like a breakdown of how agentic kind of changes versus the previous generation. So this agentic workflow, in data terms, all it means is that there's a multiplicative factor in the storage accesses throughout the lifetime of an agentic query versus a traditional straightforward pre-agentic query. You're basically causing a cascade, a chain of requests. Agents might be talking to other agents. Those agents might be talking to other agents. They might all be talking to different kinds of data platforms, S3, POSIX, file systems, RAG, vector databases, using KV caches or not, etc. And so when we run agentic, as opposed to the previous generation, we're seeing much, much more activity with respect to the storage environment. So this is my slide which says, and it's all getting worse, right? Not only do NVIDIA have the impertinence to build a faster and faster GPU with more memory bandwidth every year, but also the models are consuming that memory bandwidth with more and more queries every time there's a new release of each of these models. So there's the problem statement. So now in the last 7 minutes, let's look at just some details, some fun details. Who wants fun details of real graphs? There's one at the back. Okay. So the first thing, I mentioned this model loading. So model loading is, you have this big inference farm, and you've got all these users, massive users, and over time, there's a change in what the users are asking for. Sometimes they want small models, sometimes they want large models, sometimes they want model A, model B. So actually in a real world, these inference farms are switching models all the time. And we do get this from our customers, by the way. They call us up and say, why is model loading slow? We need it to be faster. It's a real pain. So we know it's a real actual physical pain, not physical pain, real actual economic pain for our customers out there. And so what we do, of course, is work with Run AI and other sharding model loaders and optimize how we interact with those model loaders to minimize the time taken for these models to load from the storage into the GPU memory. And here, the colors are a bit dark here. Here's what you see with local RAID, and here's what you see with DDN. So it's at around a 10 times speed up in this example. There's lots of these examples, by the way, and we could spend an hour going through these various implementations. And if you want to spend an hour going through these implementations, then I'll give you a link at the end of this presentation where you can come and talk to us about this. Lots of details. Not all of it's about DDN, by the way. Of course, we think we're really fast and efficient and we've got optimizations, but also we interact with the accelerated computing ecosystem. In this case, Run AI is doing a lot of the hard lifting here in terms of managing the sharding of these models, but we're supporting that with having a very fast parallel data path between all the storage environment to be able to push these shards in parallel to many, many GPUs simultaneously. So that's model loader. And secondly, let's have a look at this KV cache stuff. So KV cache, for the half of the audience who didn't quite get that, then I'll try and explain it. We'll do the one sentence thing. In one sentence, KV cache is, it's kind of a representation of the memory that an inference model needs to build and hold whilst it listens to your query and then answers. And if we can store that memory between every inference query, then after a time we've got this mass of historical memory, and we don't have to think again. We just go, okay, I've already thought about this, and here's the response. So that's simplistically what it is. We can remember the context in a massive storage environment at relatively low cost, and rather than recomputing and thinking all the time with these GPUs, we can just pull it from the storage environment. And what we do is we build this KV fabric, as we call it, to hold masses of KV cache that's being created through these multiple tenants, often through libraries such as Dynamo, which I think is now launched into 1.0 form, hopefully already. Good. So we integrate with these libraries like Dynamo in order to support extremely fast KV cache management in a distributed fashion. So here, just to be clear, we've got a fast software storage environment supporting maybe thousands of GPUs, and we're pushing these KV caches to all these GPUs, and we're absorbing new KV caches being computed from these things. And here's a result. Here's a surprising result. This is running a standard model on standard GPUs. Nothing's crazy. The context is quite large. It's not huge, though. And what we're seeing is over 1 gigabyte a second of writes per GPU and 6 gigabytes a second per GPU of reads. Now, what does that mean? For those not savvy, that's about maybe almost 10 times what you might expect to get from today's storage if you go for a standard reference architecture, around that. So we're seeing 10 times the current requirements in these new requirements with KV cache supporting models. And this is pre-Rubin. This is pre all this new stuff that's coming out now, pre-agentic. So this is getting really tough, and we're really excited about it because we know we can do something cool to support the demands of KV caching. And in particular, for real models, something like a 4 to 5x speed up for real world models, not kind of benchmarking, but real world models is quite practical. Imagine that. 4 or 5 times the throughput from 1,000 GPUs just by switching on a bit of magic in the storage layer. And the cool thing is, by the way, we already have this in production. So this is a report from Google. Google uses Google Managed Lustre, which is our file system provided by DDN. They published this blog about 3 months ago, maybe, basically saying, look, 70% improvement by switching on the KV cache fabric within Google Managed Lustre. So kind of almost free additional performance from your GPUs. I should start wrapping up, right? Looking at the panicked faces at the front here. So AIDP, we build Hyperpod. This is our version of AIDP. In fact, with our partner Supermicro, who provide the hardware, the networking, the GPU infrastructure, use our software, and then we support these different aspects. And I've shown you glimpses of these things today. Aspects of supporting containerized services, context, memory, enterprise RAG. We provide these services for the AI factory to make life massively simpler and to make the GPU efficiency much, much higher. Sometimes by 5x for a reasonably real-world scenario. And of course, the real reason to do that is so that our customers can move their profitability from here to here, because now they can support maybe twice as many customers, twice as many throughput queries, and the queries are essentially charged per query. And so the whole idea, of course, is not about being wonderful storage people. It's about giving our customers more revenue at the end of the day. So let's park it there. Very quick run through. If you want to hear more, we have a cool, what's called a bus. It doesn't look like a bus to me, but I come from London, where they're red and they have windows. But there's some cool stuff here. So we're running these demos I've showed you today. We're running more demos. There's a robot in there. And we've got some very technical people ready to talk to you about more details about how we actually go about accelerating these AI factories in the detail. If you're interested, or if you're not interested in the detail, we'll show you some super cool videos as well. Thanks very much.
Do we have any questions from the audience? All right. We let them access the mic.
Hi, James. Thanks for your last talk. So I have Three questions. Okay.
3.
Yeah. Okay. Yeah. The first question is that I saw there are some GPU storage controller. So my question is that if DDN is still interested about this part and maybe do some product about this part.
So do we use GPUs in the storage?
GPU controller, GPU storage controller. Yeah.
Yeah. You'll see some announcements pretty soon. So the cool thing is, we haven't talked about it here, but we have a disaggregatable storage environment. So we kind of run anywhere. We can run pieces across a distributed network in a way that's not conventionally possible. So it's like a microservices storage architecture. And so that vector embedding pipeline you saw at the first, the semantic search, anywhere that you see a benefit from, let's say, small compute, large data, we can run those containers, those storage-related containers, basically next to the GPUs to minimize the latency between GPU compute and storage access. So the answer is yes. Lots of announcements to come this year, but yeah.
Okay, thank you. Yeah, another question is that I noticed that you mentioned when you integrated with Google Cloud, you are using the file system to store all the KV cache. So my question is that from the DDN recommendations, no matter it's on a cloud or the on-premise, is the file system all the best practice for KV cache storage?
We use file system and object store. I think right now, file system is a little bit faster because it's got so many years to mature its super fast nature. But also you'll have seen maybe DDN announcing our QVS support. So it's this CUDA-RDMA object, fast object support, which now brings the gap between file system access and object access much, much closer by RDMA accelerating that stuff. So we support both object and file system. And we really have no preference. Either way is good with us.
Okay, thank you. Next question is that at the beginning, Jacoby mentioned that there are about 1 million GPUs connected to the DDN storage. So, my question is that about how many? What is the capacity of the total DDN storage connected to the 1 million GPUs?
Wow, that's a good question. Do I even know that?
You might know NERSC or just one that you could use as a...
So I know one. I don't think we can name them, but one customer which has 200,000 GPUs is running a couple of exabytes.
Exabyte?
Yeah.
Okay.
Yeah.
Okay, thank you so much.